in memory allocation. That was a broad story, how a compiler will help in memory allocation, and in how does it manages itself. We have seen by dynamic allocation and uh, static allocation, and we have seen the different methods also, how dynamically and how statically the stacks and the heaps methods are used for the allocation of the data, that is the variable or the object data items. And in the previous class we have also covered in the compilers, not this, in the compilers we have also seen how the compilation of expressions were done. And in compilation of expression I have used a lot more, many more examples. I have covered lot of examples. uh, just I will display those examples once again. So in compilation, that was a big topic, and even the memory allocation also was a big topic, which we have covered in the past 2 weeks. How the compiler used to allocate the memory for variables, and how the compiler also is helpful in allocations of the different objects or the data items during the compile time, and how the memories in the block structure using the stack was done. We have seen using the activation record. And in the last class, in the past week, we have also seen the compilation of expressions for various building blocks. What were the compilation of expressions for various building blocks? The compilation of expressions like how it was for the expression can be assignment expression, and also the expression can be the any other basic building block like for loop, or also the expression can be an array. In array the we have seen the we have seen for the indexed array means indexed base register, and we have seen various examples in abstract syntax tree, and we have also seen 2 3 examples in postfix notation, how the code was generated parallelly using the abstract syntax tree, that is called as the parse tree, and how stepwisely it used to maintain the operator precedence preference in solving or in evaluating the expression. The expression is nothing but the code for expression. The expression means the assignment operation we have seen, and I have shown just like Blackboard using the example in abstract syntax tree, and how meanwhile it will generate the code, and how algorithmically it is evaluating the computation of the expressions. And we have also seen one more example for the code generator for expressions using the we know that how during the code generation, it gives you the status of the register, also it gives you the status of the operand. So we have seen how the code was generated for a expression, and how the code was generated for a index means it is nothing but the uh, array. It is nothing but array, and how the different assignments, how the code is generated for a single statement. So this was, and we have also seen how is the cost, and we have also seen how the simple pointer variable is assigned to a variable, and also for a pointer variable how it is assigned for sorry a pointer for a pointer variable how a single value of a identifier is assigned, and what are the various steps. Steps in the sense what are the various code will generate. Usually for any assignment, first we need to move into the register. So register with for pointer to indicate, we need to use using the pointer notation for a register, and moving the content of the moving the content of the variable identifier A to the pointer register, and this is how the reverse way for from A to the register, and the cost is here also same. So such like I mean code, such different code generation for expressions. We have seen. We have seen for loop, and I have also told you for a simple statement of the expressions, and I have also told you for any assignment of the variables for array statement, and I have also shown you some various examples how does it solves for an expressions, and we have also seen what is its cost. And also meanwhile thinking I mean while solving this, it also shows you the content of the register and also the content of the address descriptor, and we have seen its status. So how the register status would be, and how the register status and how the operand status is going to be during the evaluation of the expressions. So expressions here means all the basic building blocks. Like I have told in the previous class, expressions in the all the basic building blocks. So we have seen such basic blocks like abstract syntax strip, postscript notation, and the third one was looping, a for loop, do while loop, or it can be here I have told for loop, do while loop, or it can be some conditional statements, or it can be a simple expressions, or it can expression here it can be assignment expression, looping expression, why conditional expression. So other than this it can be some, if it is a function. So how does it handle, how the compiler will handle, and how does the compiler will treat them as the expression. Based on the expression it is going to evaluate the expression and generate the parse tree, and meanwhile it will based on the parse tree, meanwhile it will generate the code. It has to manage for the code. So we have seen all such different notations in the expressions. So I was just thinking to show you how is the syllabus of the uh, how is the syllabus of the compilers which is given for your syllabus, so that it helps you to know that where I am, which topic I'm teaching, and where I am. So in the previous class, we have seen the aspects of compilation for aspects of compilation. It should not be bold. It should be this I have covered firstly. So firstly, it was covered the aspects of compilation. The aspects of compilation, something like scope rule, how is the memory allocated for data, and how the data are treated as the variable for variable, and we have in scope rule we have also seen about how the programming language will manage and will handle the bridge between the will handle the bridge between the programming language and also the and also the domain given as, I mean, some projects given. So that some projects given is nothing but the user view or the user given project. So that how does it completes in the execution domain. So using the programming language that bridges. So those were the aspects, and in the aspects we have also seen how is the scope and how is the control structure, and how all different variables will be within the program and outside the program, globally and locally, how they can be declared. And we have also seen in compilation sorry we have also seen in static and dynamic allocations the activation record mainly highlighted. The topic was on the stack. Stack was used for the sub procedures of the program, and based on the sequence of the program, how the stack will manage its procedure in the stack, and based on the procedure, how the variables will be called using the activation record. So in stack, and in aspects of compilation, the scope rules and memory allocations of different dynamic allocations also we have seen. Now today is the topic which I have to cover on the code optimization. So what is code optimization here? We need to know what is code optimization. So today is the topic for a briefing on the code optimization. So what is code optimization? The code optimization is nothing but all about the how the compiler will handle different code. Now, so far we have seen how the code was generated, and code was generated because of till up to the intermediate code. Code was generated till up to the compiler uses the compiler as it takes the high level language and generates the assembly language. That assembly language, whatever is generated, it goes with the pass 1 and pass 2 and generates the intermediate representation. That generation of intermediate assembly language, whatever the assembly language code is generated, and this assembly language code is handled by the assembler, and it goes with the pass 1 and pass 2 and generate an intermediate representation. That intermediate representation is nothing but the intermediate code. This intermediate code, how it should be. So here certain aspects I would like to tell how that intermediate code should be. How the intermediate code should be. This intermediate code should be in such a way that it should during the generation of the target code, that is during the pass 2, during the generation of the target code, the intermediate code should be optimized, should be in such a way that so that it should help in proper generation of the target code. It should help in the proper generation of the target code, so that it should remove some unwanted code, and it should remove some expression, and it should remove some dead codes which is not at all used in the program during the runtime. Why we have to do all such that compilation of the code? Because for the efficient execution of the program, there should not be any redundancy in the program. Redundancies mean something unwanted things which are some variable is there which is used for multiple times. So such things, such variables which is used in the program should be removed, because it unnecessarily increases the lengthy of the program, or I can tell it unnecessarily increases the redundancy of the program. So a compiler performs the code optimization to improve the execution efficiency. We have to improve the execution efficiency. So that's the reason the code optimization is there. One thing you should keep in mind, we are till in the intermediate representation. After the intermediate representation, intermediate code generation, this we have seen intermediate code generation using the pass 1 and pass 2 in the assembler. So till there we are. So in this intermediate code, whatever this code is generated, that should be optimized. Now in the previous class also, here I have shown you the code. this code, how it is generated for this statement, look into this code is generated for this statement. First it has to move into some register, then to that register it has to be subtracted. So this is what the code, here we cannot directly subtract, and here some compiler, what they do, it just moves the A content to some register, and also the move B content to some register, and subtract later subtract the content of B register, later subtract the content of B register by, sorry, later subtract the content of A register by B. So here one unnecessary code will be generated. So to avoid all such unnecessary codes, why we need to avoid? Because it helps in execution, proper execution in the sense very fast, efficient execution, it helps. So that's the reason we need to remove the some unnecessary codes. Let me quote here some example. If I want to do some statement, some code generation. Now in this example itself, I'll just take the previous class what we have seen. I have a statement something like A is equal to B minus, A equal to B minus C. So for this, how the code, this is a high level statement. For this, how the code will be generated? How the code will be generated? So compiler will generate a code using the abstract tree. Now it will treat this as the assignment. It will treat what is the kind of the I mean, now how is the code generation for expression? Now this is the expression, exact expression. Now here what is the expression? The expression is assignment. Whenever there is an assignment, so the compiler will check the left hand side of its operand and the right hand side of its operand, because assignment is an operator. So it start building the abstract syntax tree, and it start loading the, meanwhile it also start generating the code. Now what type, because every time I don't want to show you the abstract syntax tree for this statement. So now directly I would like to show the code. Move this uh, in register, move in this register, in R1 register, what I am moving? B. I am moving the B, variable B. And also what I am doing now, I am subtracting by C from the what? From the content of R1. So from the content of R1, I am subtracting C. From the content of R1, I am subtracting C. So in this way, so now directly again the result is stored again in R1. What is having R1? R1 is having already the value of B, or the content of B in R1, and to this R1 I am subtracting by C, the value by C. So this is how the code is generated, and later I am assigning it to a variable. That is, here I must say move register. Here I must say move to the memory location. Whatever the content is there, whatever the R1 is there, that R1 should move to the memory location. So what is the memory location? The memory location of R1 should be moved. The content of the R1, whatever the result is, whatever the stored value is there in R1, whatever the computed value is there in this register, should be moved to the memory variable. Who is that memory variable? A. Who is that memory variable? It is A. So it should be here in A. Now A is having what? The content of R1, and A is nothing but assigned by the memory variable, and A is having some addressability. So here this is what the optimized code. But most of the this is what the optimized code. But one more example I would like to show. Move the register move the register of move the register of R1, B in R1, and also move in R2 some other content, that is C. Now what I am doing, subtract in both the values I have moved respectively. So every subtract what I am telling, R1 with R2. Subtract R1 with R2. But this is not possible. Subtracting from the registers, in the registers, holding the registers value. This is not possible. So what it will do, I need to subtract some with R1 with C. R1 with C. But here the unnecessary code, which is nothing but move R. Unnecessary code, which is nothing but move R2. And here also one thing we should keep, every compiler will keep in mind, that it should try to make use of a single register. Here the two registers are used. So here the efficiency decreases and also redundancy increases, one extra code increases. So that is what, this is what it has to be removed. It has to be removed. So for this purpose, it is nothing but optimized code. For this purpose, now this is what the optimized code. Instead of now here again one more code will come, that is move M the R1 comma A. So here 4 steps are coming, but this is 3 steps is an optimized value or is an optimized code. So this is how, for this example, for this given example, what is the given statement? High level statement, some A is equal to holding the value subtracted of B minus C. So this is what the code which is generated, and this is what the optimized value. So most of the compilers, latest today's compilers will be doing the optimized code. Will be doing the optimized code itself, like Java and C++ compilers. So they all are doing the optimized code only. So here this is not optimized. So every compiler will try to have the optimized code, will try to minimize. Even it's a responsibility of a programmer to eliminate some of the dead codes, to eliminate some of the multiple use of the expressions by a single expressions. So it is also a responsibility of a programmer to eliminate some redundancies in the program itself also. So that may help during the compilation time. So it may directly take less time for execution of the program. So how manually the programmer will try to reduce the code, or will try to remove some dead code, and will also try to eliminate some of the common sub expressions wherever it is used. It will try to make use of one time. So this is all the responsibility of the the programmer to try to make as far as possible the less code. So that may help in that may be very useful in execution of the program very efficiently, and also may take very less amount of memory. So that increases, that upgrades, not degrades, that upgrades the program. So that is what the program should be the code should be optimized. The code should be optimized. So that is what today's topic, the code optimization. What is the today's topic? The today's topic is code optimization. This is what we are going to learn. Code optimization. Yes, did you got the concept? Anybody? Pooja, Pranali, four more students have left. Why we need to go with the code optimization? Why we need to go with the code optimization? Because code optimization will improve the execution. Code optimization, what does it does? It improves the execution efficiency. And what it will achieve by this? It will achieve by this. How does it achieves by this? It achieves by removing some of the redundancies in the program, by dead code removal, some unwanted code, some unwanted unused variable. So it may, and also by removing all such dead codes, unwanted variables, and the variables which are not at all used in the program. So by removing all such things, it rearranges the program. It rearranges the program, and by rearranging the program, it increases the computation to make it to make it execute efficiently, to make it more efficiently the execution of the program. So by this, what we have learned in code optimization, assume that code optimization is something, a number of, there are some number of codes. So that number of codes which are generated, we need to try to reduce them. We need to try to reduce, but this reduction should be in such a way that it should give the appropriate meaning of the program, very correctness of the program. So it should generate such correctness of the program. It should generate, it should not harm, or it should not degrade the program meaning. It should not degrade by removing such codes. It should not degrade the program meaning. That is what, and it should be very, it should keep in mind, a programmer should keep in mind that it should have the scope of the program what they want to do. So even there are some consideration. So how far we can remove some unwanted codes, or how far we can do the code optimization to improve the program efficiency based on the algorithm, based on the algorithm. So based on the algorithm, the program efficiency should be there, what the programmer wishes, what the programmer tried to do. So this all things happens at the back end of the program. This all things happens at the back end of the means programming, rearranging, removal of unwanted code. At the front end, a source code is there. At the front end, we have given the source code. At the front end, in the sense, if you remember the figure, like back end and front end, the front end is nothing but syntax analysis and syntax and I mean the lexical analysis, the syntactical analysis. The lexical analysis is nothing but the scanning, is nothing but scanning, and syntax analysis and semantic analysis. Once the syntax is right, the semantically it generates the meaning. So this all things happens at the front end of the program, front end of the program. So it is all independent of the machine. This has to happen, this has to happen. Whereas code optimization also depends on the machine. It is nothing but backend of the program which depends on the machine. So if the machine is something like very older versions, very older versions, so the assemblers during the generation of pass 1 and pass 2, it should keep in mind that very latest versions of the assemblers, like multipass assemblers, they go very directly for the code optimization, and this helps for the target code. This helps for the target code to have the minimized code, so that it can directly go for the target, or the target output, or the result. So that is what it should keep in mind. It should keep in mind, in the sense, the backend always, it is a machine dependent. The backend always is a machine dependent. Front end is nothing but up to the syntax analysis. or the syntax tree generation. Syntax tree generation. So the compiler also should keep in mind that while generating the target code from the intermediate code, it should have the optimized code. It should have the optimized code. First and foremost, you should know why we are doing the code optimization. Yes, have you all came to know, or do you all are aware that why we have to do the code optimization? Yes, just I will show you here some of the pics. Why we need to do the code optimization of the textbooks. We need to do the code optimization just to eliminate the redundancy in the program, and also by removing such unwanted codes, it also increases the execution very efficiently. Means automatically rearranges the program. That's what the code optimization will be done. Now the code optimization always in the front end, what was the, so as the source program is there, the source program as it is getting scanned, that is lexical analysis, after the lexical analysis, the syntax and the semantic analysis, and which generates the proper meaning. Once the meaning is generated, once the syntax is correct, automatically it generates the meaning. So this all happens at the front end of the compiler. So as the front end of the compiler, it generates the intermediate code. Who is doing the generation of the intermediate code? Because the compiler gives you the assembly language. That assembly language is in low level language. Low level language is nothing but low level language is nothing but 0 and 1, which the understands the machine. The assembly language, which is nothing but, which is giving you the for every high level statement, which is giving you the assembly language statement. That assembly language statement is nothing but intermediate code representation, which again passes through the assemblers, pass 1 and pass 2, where you get the optimized code. Now it's a duty of a compiler to be optimized. How does it does the optimization code? It does the optimization code in two ways, as it depends on the compiler. It depends on the compiler. If the compiler is of its own latest version, so it automatically gets passes through the code optimization phase. And also it's a responsibility of a programmer, as far as possible the programmer should try to remove some dead code. The programmer also should try to remove some expressions where multiple times they are used. Instead of that, they can use some single variable expression, some common expression, and also some variables which are not at all used in the program, should try to remove them. By this, it all removes the unwanted code in the program, and with this it try to rearrange the program. It try to rearrange the program. So this rearrangement of the program directly helps in a faster execution of the program. So this all processes is called as which happens at the back end of the process, and which back end of the process is nothing but, it all depends on the machine. So that is what machine dependent target code will be generated. Machine dependent target code will be generated based on the instructions generated during this period. Okay, have you understood? Have you understood? And how many types of, and now let me tell you how many types of, this is what which I was trying to show you. And how many types of the code optimizations will be there, or the code transformations will be there. We have compile time evaluation, we have common sub expressions evaluation, also we have the code motion, and that also we have the dead code elimination, and the strength reduction, and also we have some different methods, something like copy propagation and loop optimization. So these all are the different methods where the local optimizations will help in the variables reduction. So these all methods are nothing but the code optimizing methods, or they are also called as code optimizing transformations. They are also called as what? Code optimizing transformations. Am I audible? Yes? Am I audible? Yes, Preeti Chauhan? Pooja, thank you. Preeti Chauhan, am I audible? Pooja, have you understood? Pooja, have you understood? Hmm?
Yes, ma'am.
Okay, thank you. So these are the different methods. Which different method? This I mean some points which I have written in PPT. So these are the different methods like compile time evaluation and common sub expression elimination and code motion code strength reduction, dead code elimination, copy propagation loop. So these are some of the certain methods of optimizing. Certain methods of optimizing. So in the first and foremost, I would like to go with the method like the compile time evaluation, where you can understand very better. First and foremost, where I would like to go with the compile time evaluation, where you can understand so better. And with this method also, one thing also you can come to know, that is uh, constant folding method also will come to know. So I would like to use here in the same I would like to make some of the document as the blackboard. So here this was the one example which I have used to today's example blurly, which indicates the code optimization. This is what here, if I take the arrow sign, it indicates that how is the code optimized one. And now I would like to take here something like this is what the code optimized. This is the below one which you have got is code optimized. I would be very wrong if I write at the top. I will pick at the bottom. This figure, I mean this code, whatever I got it is nothing but code optimized. So instead of 4, I am getting here 3 line of steps, which is nothing but indicating as the code optimization, which is indicating as the code optimization. Whatever I got it, this is nothing but the code optimization, and this is what the code which is generated. Here I can also represent saying as it is nothing but intermediate IR. It is nothing but intermediate representation, intermediate code representation, or intermediate IR, intermediate representation. Whatever here I have shown in 4 steps, this is intermediate representation of the this part, the figure which I have shown you here. Here, intermediate representation, which happens optimizing during intermediate representation soon after the abstract tree generation. That is intermediate representation of the code. And further, it goes for code optimization. Further, it goes for the code optimization. That code optimization is all dependent on the backend of the machine, that is based on the compiler, based on the assembler, so machine dependent. So based on that, the target code is generated. Now could be your target code? Target code is your output, what you wanted. Based on this, the resultant is the output one. Okay. Further, this goes for target code generation. And I have told you how is the target code also in the assemblers. It only picks the R1 with R1 with memory content, or it only look into the codes. What is move? Suppose it is move is 5 and subtraction is 4 and move is 6. So it only sees the codes of that. So that gives for the target code generation. So it depends on the machine, because suppose for example assembler like 8086, maybe move R is having the value something like 05. At the same time move R may be having in 8086, it is having something like 06. It is having something like 06. So it all depends on the machine dependent. So here that is what this figure indicates from the textbook of the Dhamdre, a schematic optimization of the compiler. So what are the different methods optimizing transformations? The optimizing transformations, which I have shown you, the 6 to 7 methods, that is compile time evaluation and common sub expression and code motion and the strength reduction, dead code elimination, copy propagation and loop optimization. Loop optimization. So in a loop also, if for a loop something like for loop, do while loop, so for that loop also how we can optimize it, how we can make it to the lesser one, how we can make it to the lesser one. The very first and foremost, which I would like to make it again use of as the blackboard. So I would like to come up again with the compile time evaluation. How is what is called as the compile time? Compile time evaluation. What is compile time evaluation? This can be understood very better by making use of one example, which I want to show something like this. The compile time evaluation, one thing you should understand, this is the compile time evaluation during the time of compile time. During the time of compile time. I think you have understood here who can be called as the compile time evaluation. The value which you give during the runtime of the program, the value which you give during the runtime of the program is called as the compile time evaluation. The value for what? The value for some certain identifier what the compiler is asking for you. So during that time, the value which you give during the compile time. So those value, that value directly it goes for computation, directly that value goes for the computation, and here it reduces the subtraction or some computation, because you are giving some direct value, it reduces some computation time, it reduces some computation time. Suppose if you are not giving the value during the runtime, maybe the compiler is taking from the program itself only, making some arrangement, making some computation from the program itself. Suppose we have a value something like 22 by 7. What is this 22 by 7? What is this 22 by 7? 22 by 7 is something like a value. What does it gives? You may be knowing what is the value of the 22 by 7. And even 22 by 7 is nothing but it gives you the value 3.1415 and so on and so on. But I am just giving something like this only, a hint I am giving you. You may know that, but what is this? What for? What for this value we are using? Where 22 by 7 is nothing but a value of the pi. You know it very well. You know it very well. What is pi? Pi is 22 by 7. Pi is nothing but 22 by 7. If suppose this value is given for some calculation, if suppose this value is given for some calculation, what that calculation is something like I have to do some area calculation. I have to do some area calculation. So for that area calculation, I need something like this, where I want to do this pi value to be divided by 2, where this pi value to be divided by 2, to be divided by 2. Now what it has to do, if suppose if you're not giving, if you're not giving what is the pi value to the compiler or to your program, what it has to consider, it has to consider whatever the value you have given in the program. But at the same time, instead of pi, you're giving something like this. So this value, you're giving something like this, 22 divided by 7 and whole divided by what again, 2. Whole divided by what again, 2. So now the compiler, what it is doing, compiler has to do first the computation for 22 divided by 7. Compiler first it has to do the division for 22 divided by 7. Then it has to do division divided by 2. So for this, instead of this, if you give during the compile time itself only, during the compile time itself, if you give the value something like this, where directly calculated value, so far from the childhood days we are learning that pi value is pi value is something like 22 divided by 7, and its value is something like floating value of 3.1415. So since from this value we know it, so directly if you give the pi value, that is 3.1415, which is divided by 2, now compiler has the duty, because compiler is asking you a value of pi, you're directly giving something like 3.14. So compiler here it is reducing the computation of one division. Here it is reducing the computation of one division. What is that computation of division? That is 22 divided by 7. So in this way, it is only doing a computation of 22. In this way, it is doing only a computation of 3.14 divided by 2, where you may get the value something like this. 1 point, I think you are calculating. I want the meanwhile students also should do something like this. Maybe you will get something like this, if I am right. Yes, am I right? So you may get the value something like this. So what is happening here, it is replacing or it is eliminating some of the division operation. What it is doing, it is eliminating some of the division operation. What is that elimination of division operation? One division operation we have reduced, that is 22 divided by 7. Directly its value we have given during the compilation time, that is 3.1415, we have given like that. So for this, it is also called as folded. What folded value? That folded is nothing but constant folding. It is also called as constant folding. This constant folding is nothing but a primary method of optimization, where it happens. From this only it is learned, or from this only it has come to the term something like this. It is called as constant folding. What it is called here, I would like to write the term something like this: constant folding. Why it is called as constant folding? Why? Because only one division operation is handled here. Only one division operation is computed, and that too during the runtime. Runtime in the sense, now here it will not generate any other computation. It will only do the computation for 3.145 divided by 2. So this computation performs only during the execution of the program, and this would give you more exact efficient for which the compiler needs, means it increases the fastness of the execution of the program. So this concept is also called as the constant folding. where we have learnt here. Constant folding in the sense always something, some values. There are some values where certainly directly the user gives. The user directly gives them. That is 3.14 is what? 3.14 1415 is nothing but 22 divided by 7. We are not giving to the computer 22 divided by 7. Have you understood? Sorry, we are not giving to the compiler 22 divided by 7, only we are giving 3.14. Yes, have you understood, Pooja? Yes, Pooja, have you understood? Any other student? Yes, Deepti, Onkar. Today Onkar is not there. Pranesh has left. Naveen, Madhura, Prashant. Onkar is telling who, madam? Thank you. Naveen, Prashant, Pratik, Radhika, Manashri, Gaurav. Why you are leaving? If I ask something, your people are leaving the class and again you'll come at the end. Ma'am, I was not having the connection. You'll tell like that. Have you understood? Constant folding. Constant folding is nothing but it's a concept, something wrapping the computed value and directly giving during the compilation time. Constant, and for this, which we call it also a primary optimization, which is a basic optimization of the programmer for a compiler. Okay, like this only we need to give to the as far as possible. A programmer should try to give to the compiler the computerized value during the compile time. So that concept is also called as the is also called as what? The constant folding. Yes, have you understood? Okay, now another one, if you look into this, another one, we shall study about the common sub-expression elimination. What is the common sub-expression elimination? So the constant folding which we have seen here, but something like this which I have shown here using the arrow marks. Okay, the now another one we shall study, that is the common sub-expression evaluation, which I tried to show you from the textbook, and what the textbook also says, you must be known some of the examples. This is the loop optimization example. This is the strength reduction example. This one, I would like to just download this. Okay, the common sub-expression here, I have certain example, something like this. A is assigned by multiplication of two operands, that is B and C, where again B is further multiplied in some computation to seek the value for x, So how this can be optimized? So certain programmer will try to make use of multiple copy, not multiple time of using of such a sub expressions in the program. So it's a programmer duty that the programmer should look into in such a way that he should try to minimize as far as possible the code, as far as possible the statements to be written. So here first and foremost, here two sub expressions seems to look like same. Two sub expressions seems to look like same. First expression, that is b was multiplied by c, and again the b multiplied by c was again used in another expression. So we need to try to do something like we need to make here some common substitution. So that is what it is called as common sub expression eliminations, where this can be done in this way, where b, which is multiplied by c, should be assigned to some variable, temporary variable, assigned to some temporary variable. So again that t should be utilized, again that t should be utilized, so that t is nothing but it it substitutes, that t is nothing but b is multiplied by c. It substitutes that t is multiplied by c. This is how one another kind of substitution, where some expressions are, substituted by using some common substitution method. This occurrence of the twice occurrence of such an expressions should be identical, so that it can eliminate such a big expression into some small expression. So here the occurrence of b star c can be done at once only, can be done at once. And here one another way also is there, another way also can be done. Instead of another way also can be done, instead of assigning it to some temporary variable, directly we can take this a also directly, and we can multiply here, sorry, we can substitute that a here, we can directly also substitute that a here. But it gives us the problem during, the code optimization, because during the code optimization, here what does it happens, it has to move the content of b to some register, and it has to do the multiplication to that register by c, move the content of b to some register and multiply to that b, multiply to that register by c, and hold the resultant in the register, so that register value should be moved to some temporary variable. So that is the reason we need to take here. You should not think only from the high level language view. We should also try to think from the assembly language view, because after all the compiler converts the high level language to assembly language. So for here one can think that instead of taking here temporary variable, directly we can compute that a here, we can compute that directly the value of, instead of t a here, unnecessary one t assignment is increased here, one can think in that way. But this is required. Why this is required? Why? Because we make a use of single register, that is what this is required. So this is how it looks like code optimization, optimized code, as the code look like this. So after the optimization it looks in this way. So this is required, and this would be executed And this would be executed to increase the efficiency of the program. So this may increase the efficiency of the program during the execution time, that means during the runtime also, and hence the compiler transforms such a program to the form as shown here, in the assembly language. And here, the value whatever it is computed for t, which is nothing but the resultant of the multiplication of b and c, would be saved in this temporary location, and later it can be used to the assignment operation during after computation of this addition, and it can be assigned to c. So this had in this way, that's what where temporary variable was used for here. So this is how the common sub expression, and the same common sub expression I have just taken here also the same thing, but not of the uh, decimal value. So second example, also some other examples also you can see here. Some common sub expression eliminations, how they can be done. Some C is here. So for C, we need to pass it to the temporary variable, and I have passed here, and again somewhere a plus b was used here. So that a plus b, whatever it is used here for f, so it is told as t1. Suppose it was t1 here. Of course, it was t1 here, and again here for mn, again here the mn value is assigned, the multiplication value is assigned to k. So this would make an substitution as t2, uh, for the assignment to d. So the same value which is assigned to k. So this is how the some expressions in a program can be eliminated, and they can be used further for substitution, where the program where the code is necessarily making use of such subterms. And here also one more thing is there used as b plus d, and this b plus d already was already assigned to e, and here it can be called by t3. And we can make use of, but by going such temporary variables more and more, it may also lead to some unnecessary redundancies of the assignments. So whatever is the availability within that itself, we need to try to not. Here overall I had made only the two availability of the temporary variables, one is t1 and the other one is t2, so here we had made for h b plus a, b plus a b plus a was already told as a plus b, so that's what again it was used as cumulative. So we should not be I mean the compiler should try to make use of such a such an assignment expression, where it should use some the cumulative methods also. It should try to understand that a plus b is nothing but b plus a only, so it should try to apply here the cumulative type of the assignment expressions. So here one more expression, that is b plus d was made as 3, and this b plus d, which is nothing but an nowhere used, so that's what it is, a new assignment, nowhere used in sense nowhere earlierly temporarily it was used, so it is a new one, so it is a t3. So it will, a compiler also will look into in such a matter that whether is there any variables which are computed already, so it will just check that. If it is not there, if it is no such sub expressions are not present, means it will just allocate by a fresh temporary variable, that is t3. So it is t3. Now a is equal to minus b, so a is equal to minus b. As far as possible, the compiler will try to make out the we try to make out the possibility of sub expressions, evaluating by common sub expressions, evaluating by common sub expressions. So with this evaluation, with this evaluations, what does it happen? So we can rearrange the program and we can execute the program very efficiently. We can execute the program very efficiently. By this common sub expression evaluation, the compiler, by implementing such a method, what it does, anyhow, the main motto is nothing but to increase the efficient running of the program during the execution time. So that is the main motto of the program. So here, by doing like this, the common sub expressions, but it is a compiler headache that it has to identify the number of temporary variables. It has to identify the number of first it has to identify what are the new expressions. Those new expressions that it has to, for every new expression it has to generate a temporary variable. So in this way the compiler should keep in mind that for every new expressions it has to generate an temporary variable, and later that temporary variable should be used wherever necessarily it is called in the sub expressions. It should substitute only that temporary variables. So this is how the common sub expression does the occurrence of the sub expressions which satisfies the criteria of saying as the expressions should be eliminated. Why directly it cannot be used? One first and foremost questions: why it cannot be directly used? It can be directly used. Why? Because again unnecessarily the assembly code will be increased. Unnecessarily the assembly, because suppose here a plus b, again the code should be called for move this a to some register, again add to that register b. So unnecessarily code will increase. That is the reason to avoid such unnecessarily code which already has generated the code for a plus b. Now it has to substitute here. Now it has to substitute here. So that is the reason it has to substitute some common sub expressions in the eliminations, because to avoid again redundant generation of the code during the intermediate representation. When does this intermediate representation happens? This intermediate representation happens after the syntax tree generation. The intermediate representations of the code generates. So multiple time generating the same code, again calling the same register where the previous value will be replaced by again the new value, but after all it is doing the same work. But for this f, so instead of that we can directly put here to f the computed value of c, which was in temporary variable t1. So f can be assigned by t1. So how the compiler will try to solve in such a multiple sub expressions? The first the compiler will try to identify, is there any new expressions? If there are new expressions, it start generating the assignment. It assigns to temporary variable. First it identifies where the expression would be the new one, and if it is same, it start assigning the same value. By this same value during the execution time. So by this here the code elimination is done. And also this part of the time is also reduced during the compile time. Here also this part of the time is also reduced during the compile time. So directly it can substitute that value during the compile time. Directly it can substitute the value of T1, T2 and T3 wherever it was necessarily be called during the compile time. So this is how the common sub-expression elimination. Common sub-expression elimination. Hope you have understood. Yes, have you understood? So one more example of common sub-expression elimination which I have shown from the book. This is how the common sub-expression. So common sub-expression elimination which we have seen why such common sub-expressions should be done, because again and again it should not generate the same code for the same type of expression, for the same type of expression. So that is the reason it should substitute commonly. Yes, have you understood? During the time of attendance, again the strength is increased. Have you understood? Puja, Onkar, Onkar, have you understood? Today we have learned two methods. That is common sub-expression elimination, and before that I have told compile time elimination. I have told about compile time elimination, and in that we have learnt about constant folding. What we have learnt? We have learnt about constant folding. Why common sub expression should be eliminated? Common sub expression, sorry. Why there should be some substitution of some expressions? There should be substitution of some expressions if the expressions are common, because again and again during the intermediate code time it generates the same code. So this increases the redundancy. Now suppose for this F also it generates the same code. What was the code for here? The code here it was, I'll try to write here itself. First it will move the register, move the register to R1 A, to R1 A. Then what it has to do? Add to this R1 by B, and the result is in R1 only. So this part of the code, again it will be generated for this part. Again it will be generated for this part. So what it will do? It will keep temporarily move this R1 in some temporary variable. Move this R1 in some temporary variable. Who is the temporary variable? T1. Now here what it has to be done? Now here what it will happen? Instead of this where it was called multiple times, now here I can call only to this F. I can only to this F I can call by T1. I can call by T1. So what I will tell? Move to this memory content of T1. What is holding the T1? T1 is having in R1. T1 is having in R1. So I can just tell R1, but T1 will be assigned to F. T1 will be assigned to F. But both the memory locations cannot be possible. So first I need to move. The computed value of this is in T1. The computed value is in T1. So I need to move this T1 to some register. T1 to some register R1. So in this way it can happen. So it eliminates here two statement. Move R1 to A and move R1, add R1 by B. So it eliminates these two statements. So in this way, the common sub expressions will be used. The common sub expression can eliminate the code, can eliminate the generation of code. Yes, have you understood roll number 1?
Yes, ma'am.
Have you understood?
Yes.
2, have you understood?
Yes, ma'am.
Okay, two topics we have learnt. One is compile time evaluation and the other one is common sub expression evaluation. Sorry, common sub expression elimination. So those two topics we have learned, but still we have many more. We can study them in the next class. Another three methods are there for code optimization. Another three methods are there for code optimization. So just give me your attendance. Onkar, have you understood? And one thing you should keep in mind, why code optimization is done. The code optimization is done for making the program more efficient. And how we can make the program more efficient? Because by removing some dead codes, by removing some unnecessary variables, it reduces the number of steps in the program, and by this it rearranges the program. By rearranging, it shortens, means it optimizes, and this would help for fast execution of the program. Fast execution in the sense, we just say it as efficient execution of the program. And one more thing, by removing such a redundancy, it helps the program for the compiler. It helps during the target code generation directly. Codes are generated which optimized codes are generated that would be more optimized in the result. Means indirectly it is nothing but efficient generation of the program. Efficient generation of the program. As far as possible, we should try to reduce the code, and as far as possible, we should try to make the compiler to not to do more compilation. Not to do more compilation, because it wastes. Just now we have seen one example. First it has to calculate 22 divided by 7. Then it has to do division for whatever that 22 divided by 7, whatever its result, it should be divided by 2. So we have reduced there one division method. We have reduced there one division method. So in this way, we have to give to the compiler the the reduced one. A reduced one in the sense, it should do something like computation should be reduced. So this is what the main motto of the program. Have you understood all? Yes. Give me your attendance. 3,
Present, ma'am.
4,
4
5,
present, ma'am.
6,
Present, ma'am. Roll number 5 is present.
7,
Roll number 6 is present.
7, 8, 9,
Present, ma'am. Ma'am, roll number 8 is present.
10. Okay. 10, 11,
Present, ma'am.
12,
Present, ma'am.
13,
Present, ma'am.
14,
Present, ma'am.
15,
Present, ma'am.
16,
Present, ma'am.
17, 18, 19,
Present, ma'am.
20,
Present, ma'am.
21,
Present.
22,
Present.
23,
Present, ma'am.
24,
Present.
25,
Present, ma'am.
26,
Present, ma'am. 26.
27,
27 present, ma'am.
28,
28. Present, ma'am.
29,
Yes, ma'am.
30,
Yes, ma'am.
31, 32,
Present, ma'am.
33,
Present, ma'am.
34,
Yes, present.
35, 36,
36. Present, ma'am.
37,
Present, ma'am.
38,
Present, ma'am.
39, 40,
40 present, ma'am.
41, 42, 43, 44,
Yes, ma'am.
45,
Present.
46,
Yes, ma'am.
47,
Yes, ma'am.
48,
Present, ma'am.
49,
Present, ma'am.
50, 51,
Present, ma'am.
52, 53,
Present, ma'am.
54,
Present.
55,
Present.
56,
Present.
57, 57, 58,
Present, ma'am.
59,
Present, ma'am.
60,
Present, ma'am.
61,
Present.
62, 63, 64,
Present, ma'am.
65,
Present.
66, 67. Hello, madam. I'm in class, madam. हाँ madam. After this class, I will be. Madam. 66, 67, 68,
Present.
69, 70.
Present.
Okay. 18, 31, 35, 39, 41, 42, 43, 44, 50, 57, 61, 62, 63, 66, 67, 69 are absent. Let me know. Have you done the gate registration? Yes. Have you done the gate registration? Okay, you can send me personally. I request all the students to send me personally the number of gate registered students. Because now HOD ma'am is asking, please send me personally.
Roll number 44 present.
Have you done the gate registration? Please send me gate registered form uh, so that I can give count to the HOD ma'am. Send me personally, okay? The gate registered student. Yes. How many of you are gate registered? Okay, thank you all. Maybe you don't want to tell here. So you can register me post personally.
Roll number 41 present.
Have you registered for gate? You're telling only your roll call. Have you registered for gate? I'm asking you something, okay? I will give you attendance. Have you registered for gate?
No.
Why you don't belong for gate registration? Okay, no problem. I'll mark your attendance.
Ma'am,
If any
17
students
present.
have registered the gate, huh? Okay, dear 17, have you registered for gate?
Not yet, ma'am. I'll register today.
Because madam is asking me the gate registration forms. How many of you have done in your class? I have also forwarded one link to those who have registered can forward your forms in that. I have told in that way, but nobody have done, I feel. Okay, I will mark you. 17 you are present.
44 ma'am.
44, have you registered for gate?
No ma'am.
Why? I will give you attendance.